This is Earth Science in the fall of 2025. This is the notes and discussion over the volcanism and mountain building unit or chapter. And today we are going to be discussing the volcanism chapter of this unit. There are different types of volcanism. One of them is a convergent volcanism, and that occurs at subduction zones where the subducting plate subducts underneath the overlying plate, and then it reaches the point of partial melting. The partial melting causes the melted magma to rise up to the crust and then poke through the overlying plate and create a volcano. These volcanoes are normally very explosive, and even though they're explosive, less magma is produced. And we'll learn about this later, but they normally have andesitic magma, which has intermediate viscosity. And then most of the volcanoes on land result from this. So examples of this could be the Andes. There's volcanoes in the Andes Mountains, or all the volcanoes that are along the Rocky Mountains in the northwestern United States, like Mount St. Helens, are good examples of that. So there are two areas where these volcanoes occur a lot, and the big one that you've probably heard of before is the Pacific Ring of Fire, and this is also called the Circum-Pacific. So circum means around, Pacific is the ocean, so it's around the Pacific Ocean. And this is where the Andes Mountains and here are the Andes Mountains, and the volcanoes that would be connected to the Rocky Mountains over here. And there also, if you notice here, would be the Mariana Trench, the Aleutian Islands, they're also part of that. And the other ring or belt that these volcanoes rapidly occur in is called the Mediterranean belt. So this is the belt that is right around Italy, and Vesuvius and Etna are two pretty well-known volcanoes in that area, and this is caused from the movement of the African plate, which is this big plate here, crashing into the European plate. And these all, once again, create very explosive volcanoes. They can do a lot of damage. And then the second type of volcanism is divergent volcanism. These occur at the mid-ocean ridges. They have calm volcanoes, but they also create lots of magma. They're calm because the plates are spreading apart, and when the two plates are spreading apart, it just leaves a gap for the magma to slowly fill in the gaps, okay? And they create something called pillow lavas. These pillow lavas are basaltic lava, which means they have low viscosity, and basaltic because it's ocean plates, okay? So an example of this would be the mid-ocean ridge that is separating, slowly making the Pacific plate grow bigger. The last type of volcanism is hotspot volcanism, and these are volcanism that occur far from plate boundaries. And if you remember from the previous unit, the hotspot is created by a magma plume that is stationary in the mantle. So this magma plume does not move at all, and then the plate moves over the top of it, and the magma plume is able to eat away at the plate that is over the top of it and create a volcano from that. So these hotspot volcanoes often create flood basalts, and two examples of flood basalts are the Columbia River basalts, which are actually in the United States, which is connected to the Yellowstone caldera. This map down on the bottom right, the little circular things that are going to the top right, Snake River Plain hotspot, that is the Yellowstone caldera. And then the Yellowstone caldera is thought to have produced the Columbia River basalts long, long ago. And another example of this is the Deccan Traps, which is in India, just a very big river or flood basalt. These types of volcanism normally have rhyolitic magma, which is a very high viscosity magma. And then another area in the world that hotspot volcanism has created volcanoes is in the Emperor in Hawaii seamount chain. So this is the picture that is in the bottom left. And as you can see, this one is created on an ocean plate, whereas the Columbia River basalts and the Deccan Traps are created on a continental plate. But as you can see, the long string of islands in these two chains, the magma plume stayed stationary, and then the Pacific plate slowly moved, which created each of these islands, each of these volcanic islands. So we're going to move on to the volcano anatomy of a volcano, and it is pretty simple. A magma chamber is the part that is storing the magma from the mantle. So it's this hollowed out cavern, basically, under the volcano. And then the lava is pressurized enough that it flows up into a conduit right here, kind of a vent or a chamber is what I would normally call it. And then it flows out into a vent right here at the top. And then there are things that, like a side vent, some volcanoes have a side vent where a volcano goes a different route out of the volcano, or magma goes a different route out of the volcano. And then caldera, this is this picture on the right. And a caldera is a very big gapping hole in the volcano that is created from the volcano having a very explosive eruption at one point in time, and then part of the wall crashes down into the newly opened vent, and then it creates a very big like crater type thing. And this picture is a picture of Crater Lake, which is in Oregon, I believe, and it is a lake that water slowly filled into a caldera from a blown out volcano. Okay, volcano types. So there's three main types of volcanoes. There's other ways that you can classify these, but they are the cinder volcano, which has normally pretty even sides, but they're pretty steep. Steep but even sides. This is the one that's shown on the left. And then composite volcanoes are the ones that have very steep sides, like concave sides. And these, both the cinder and the composite volcanoes, are the ones that have the most explosive eruptions when they do erupt. And then a shield volcano is the biggest volcano, but it is also the most gentle sloping one. It almost has convex slopes, and most of the time it's hard to even tell it's a volcano because they're so big it just looks like a very big hill. But they are the biggest volcano, whereas the composite is like the middle-sized volcano, but it is very easy to pick it out on the horizon most of the time because it's very sharp sides. And then a cinder volcano is the smallest. A shield volcano normally has very easy non-explosive eruptions also. Here's some more of the information from it. So shield volcanoes are the largest, gentle slopes, quiet eruptions, built by layers of basaltic magma. That's how you get that convex almost sides. And this picture that's on the top right is a picture of the Hawaii volcano. And as you can see, it's this thing that's clear on the horizon. You can hardly tell that's a volcano because it's just so big and it's so sloping. The sides are slow sloping. Okay, and basaltic magma. And then the composite volcano is the middle-sized volcano. It is very tall and kind of imposing looking, and then it has explosive eruptions that also help build the sides of the volcano. This is a volcano. The bottom right picture is a volcano on one of the islands in Alaska. And these have very explosive eruptions, as you can see from the smoke that is billowing out of it. And then the last type of volcano is the smallest, and it's called a cinder cone. These are really steep sides, but they're normally pretty evenly sloped. They're not convex or concave. They have explosive eruptions, and these are normally seen along with another larger, another larger volcano. And they also have basaltic magma. So extrusive activity, which is this word in the middle right here, is the word for outside of the volcano, activity that happens outside of the volcano. So that could be like eruptions, okay? And then later on we'll learn about intrusive behavior, and that is activity that happens inside the volcano. So many things can help determine the type of eruption that it will have. And one of these is temperature, another is pressure. Dissolved gases is the main one that determines how explosive it is. And then viscosity. So temperature, different types of rocks melt at different temperatures. So if you have a very light element magma, it's going to melt at a lower temperature than a very dark element magma. Pressure, and if you remember from also the previous chapter, as depth increases in Earth's crust, as depth increases, pressure increases, and when those two increase, that means the temperatures of melting for these rock types also increase. So if it's deeper within the crust, the melting temperatures are going to be higher. And then dissolved gases. Depending on the type of material the magma or lava is made out of, depends or kind of determines the amount of dissolved gases that are inside of the magma or lava. And if there are a lot of dissolved gases, that increases the explosivity of the eruption, because the gases try to escape from the magma, which creates popping sounds, and and then viscosity. So high viscosity is able to trap gases more. So high viscosity is the one that moves very slowly. It's like very cold honey would be a good way to think about that. It's sticky, it moves very slowly. Or slime would probably be another way to think about it. It just moves very slowly. And then low viscosity has a low silica content, and I would describe that as like a hot, like you warm up honey or you warm up syrup, and it creates or causes it to run very fast and spread out very fast. The low silica content means that it does not trap gases, and then it has calm eruptions, whereas high silica content traps gases, creates explosive eruptions. So basaltic lava, these are the types of lavas that are commonly found in volcanoes. So basaltic lava has less than a 50% silica content. It has low viscosity magma. It does not interact with crust or sediments as it's coming out of the volcano. And since it has a low silica content, gases escape very easily. And since gases are able to escape very easily from the magma, then there are quiet eruptions. And then andesitic lava is, sorry, kind of the midpoint between these two. So you have a 50 to 60% silica, which means it has a medium viscosity. And these commonly occur at oceanic continental subduction zones. So rhyolitic lava has the most silica in it. It has a high viscosity, which means it moves very slowly. So like cold honey. And since it moves very slowly, it's able to trap gases, which create explosive eruptions. So, intrusive activity. I said earlier that we were going to be learning about activity that happens inside of the volcano, and these are called intrusive activities. So, intrusive activities create plutons, and there are several different types of plutons, which we're going to be talking about. And plutons normally have coarse-grained texture. So, what does coarse-grained texture mean? Coarse is like big grained texture. And that is often created by or affected by the depth and temperature that the grain size or that the magma started to solidify. So if it's deeper within the Earth's crust and mantle as it's starting to solidify, it has more time to solidify, then it will have a more coarse-grained texture. Now, if the magma or lava is solidifying very close to the surface of the earth, so outside of the volcano or just at the very tip of the crust, then it's going to have finer grained texture. Okay, so types of plutons. There are 5 main types of plutons. A batholith is a big irregularly shaped pluton, and it's shown in this very big greenish gray area down here. They're big. They could have been like old magma chambers, perhaps. This big and irregular shaped. So the next one is a laccolith, and a laccolith is pretty similar to a batholith, but it is lens shaped, so it's convex, and that's shown up here on this one. And a laccolith, the magma fills into the rock layers from a crack or whatever, and it slowly pushes up the other rock layers that are above it. So this creates this condensing right here, compression force, and it could also create little humps in the crust, like outside in the crust. And then a sill is shown right here, and it is a pluton that fills in gaps that are parallel to the rock layers. Okay, so it finds a fissure in the rock and then it fills in parallel to the rock layers. Okay, they're usually pretty small, kind of skinny looking, and then dikes are very similar to sills, where they're just a line most of the time, but they fill in fissures that are perpendicular to the rock layer. So sills, you got the sill here and then the rock layers, and then a dike goes perpendicular, so at a 90-degree angle. It doesn't have to be 90 degrees, of course, but like across. Okay.